Hi there, Professor Venus here with chapter 12. Let's start solutions. I'm not going to work on every single detail or PowerPoint slide because it's going to take a long time. But I will go over the concepts. Whichever concepts you will have in the videos and the PowerPoint slides, you should expect them in the exam. Other than that, don't worry about the concepts that are not included in your videos and the PowerPoint slides. So let's start. I will divide the chapter lectures into more than one video because I don't want them to be so long. So let's start with the introduction, the terminology of this chapter, and let me adjust the camera. All right. You know, this is not the best condition for lecturing and not the best board, but what can we do? All right, so chapter 12 is about solutions. What we need to know is what is in each solution. In each solution, you have two different components, solute and solvent. What is a solute? This is the compartment that, change my marker. This is the component that exists in smaller amount, and solvent exists in the larger amount. There are different types of solutions. When we talk about solutions, you may just remember the solutions of water, but we can have solid, liquid, or gas solutions. But here, of course, we are talking about the liquid solutions. So, for example, let me just give you an example of a liquid solution. When we talk about let's say Coke, a glass of Coke, what can be the solute or solutes? We can have more than one solutes. I'm sure that you will say in a glass of Coke, the solutes are going to be carbon dioxide, sugar, lots of sugar in Coke, and color. Or maybe the rest of the stuff that we cannot taste. And the solvent, I am sure if you were with me, you would say solvent is water in a glass of Coke. You can also have gas solutions. In gas solutions like air, solvent, what is the component in the air which is most abundant? Nitrogen, right? And the solutes can be oxygen, carbon monoxide, carbon dioxide, and the rest of the gases, depends on where you are. And also you have the solutions of solids. In solids, like coins or alloys, in alloys, you have different components, depend on which coin you're talking about. You can have copper, you can have zinc, you can have a little bit of iron. So these are the different types of solutions. I told you we talk about the solutions in which the solvents are liquid, mostly water, and we will first get familiar with their terminology. Another term you need to know about the solutions is miscible and immiscible solution. Or I always say miscible, that the word is similar to mixable. So in miscible, you have just one clear phase, just like when you add alcohol, rubbing alcohol or drinking alcohol, ethanol, to water. You just see one phase, one clear solution. But when they are immiscible or immixable, you have more than one layer, more than one phase. like when you add vinegar to oil to make vinegar dressing. Which one stays on top? I'm sure you would say oil, because oil has less density. Okay. Another terminology about solutions is the amount of solute. Let's call it unsaturated, saturated, and supersaturated solutions. So we all know the meaning of the word saturate. When a solution is undersaturated, let's talk about the solution of salt and water or sugar and water. Let's say you're in the kitchen and you want to make some sugar solution. So when it's undersaturated means the amount of solute, the amount of the smaller component, which is sugar here, is less than in a very simple language, less than enough. What is enough is the saturated solution. So what is a saturated solution? In a saturated solution, it's solute is in equilibrium state. So what do we mean by equilibrium state? Because when you add sugar or salt or any other solute to the solvent, it takes some time. If you have noticed, it takes some time. You need to mix it with a spoon. We need to take some minutes, some seconds, let's say, to let them dissolve. Why? Because the solute, sugar or salt, you know, they're in the form of crystals, right? It needs some time. They need some time to overcome their lattice energy. Lattice energy. You have it in this chapter. In lattice energy. Lattice energy is the energy that you need to spend to overcome to break the structure of this crystalline sugar or salt or any other solute that you have. You need to overcome their breaking their structure. So we have a lattice energy and we have hydration energy. Hydration energy. Let me to explain it more. So for the lattice energy, let's say this is a cube of salt or sugar. And you have more of these cubes in a crystalline structure. So there is an energy which is called lattice energy to break this structure. Let's say you have more cubes everywhere around this cube. So you have to wait until this crystalline structure collapses. And then at the same time, let me talk about NaCl. So let's say we broke Na and Cl finally. We broke this crystalline structure. Now we are dissolving them in water. So now water molecules come. You know, water molecule is a polar molecule. Partially negative charges on oxygen, partially positive charges on hydrogen. So there are some weak intermolecular forces between oxygen with a negative charge and with sodium with a positive charge. At the same time, around sodium ion is full of water molecules. It's not just one, plenty of the water molecules. And also around chloride ions, chloride has a negative charge, so intermolecular forces will be between, they're polar, right? Dipole, between chlorine and hydrogen. So this is called hydration. So we first need to overcome the lattice energy, and then the hydration energy is going to work to dissolve the solute. So we're talking about an ionic compound, so lattice energy is for ionic compound. So depending on how big the lattice energy is, you probably need to wait more to dissolve. The stronger, the more time you need to overcome the lattice energy, and then the hydration happens. When we talk, going back to our original discussion, saturated solution, when we talk about saturated solution, means this solid, let's say this is solid, and these are the ions, there should be an equilibrium. So the amount of solid that goes to the liquid phase is in equilibrium with the ions that go back to the solid phase. It's in equilibrium. So in saturated solution, you have dissolved maximum amount of solute that you could have dissolved in the solvent. So when the rate of forward, the speed or rate of forward, you will learn more about the rate in the next chapter. Rate of forward reaction becomes equal to rate of backward reaction. We call it equilibrium. So in a saturated solution, these two rates are equal. You have dissolve maximum amount of solute in the solvent. And finally, if you try to dissolve more, supersaturated, if you try to dissolve more solute in the solvent, more solute than equilibrium state, or more than saturated state, then you call it supersaturated. You normally make a supersaturated solution by increasing temperature. You can easily, it's safe enough to do it in the kitchen. Try to dissolve some salt or sugar in water in room temperature, in the kitchen temperature. And let's say you have added 2 grams and you already made a saturated solution, and you will see that some solid starts forming. Increase the temperature, you will see that solid starts dissolving. So by increasing the temperature, you can dissolve more and more. Because why? Because the motion of the molecules in the liquid phase increases, the hydration energy increases, and then you can dissolve more. But if you leave that solution to cool down, you will see the extra solid that you have tried to dissolve goes back to the solid state. I'm sure you have experienced it in the kitchen. Sometimes you have made some sugar solution or salt solution or any other solution by dissolving an ionic compound, and then you will see after a while the crystals are formed. That's because by cooling down, the extra solid has gone back to the solid phase. So that's about the solubility and saturated, unsaturated solutions. Another thing you need to know about the solubility, and what is solubility is the amount of solute that you can dissolve in the solvent. You must keep this golden rule in mind. Like dissolves like. We all know it from school days. What does that mean? Means that the compounds with, you remember intermolecular forces from Chem 1? Means compounds of similar forces will dissolve in the compounds with their similar So basically, like let's say you said ethanol, CH3, or let's just go with alcohol. Alcohol is miscible or mixable in water. Why? Because both of their intermolecular forces are similar. If we talk about ethanol, and you don't need to know the formula of ethanol, you will learn it in the last chapter. You will see that they can form hydrogen bonds. You cannot dissolve ethanol in carbon tetrachloride because it's non-polar molecule, carbon tetrachloride, and ethanol is a polar molecule, so they are not miscible, they are immiscible. If you could go to the lab and you would try to mix these two, you would see a 2-layer solution here. Okay, here this is the terminology of this chapter. In the next video, I'm going to talk about the concentration of solutions. We still have some time. Let's finish this part with Henry's law. I told you I don't want the videos to be too long, but we still have some time for this video. It's not that long. So Henry's law, when you talk about gas as solute and liquid, mainly water, as solvent. And it should remind you of soft drinks, like a soft drink, like Coke, Pepsi, sparkling water. Okay? Here's the formula for Henry's law. By the way, in the exams, the formulas for each chapter will be provided. I don't want you to be worried about memorizing them. You will have them and you just need to know how to work on them. So S is the gas solubility or just solubility. KH is Henry's constant. And P is the partial pressure of gas over the liquid. So whenever you're talking about the solubility of a gas in a liquid, you need to use Henry's law and keep this example of soft drinks in mind. And you can also imagine a cylinder full of liquids, and not full of liquid, like halfway with liquids. Let's say this is your liquid, and some gas molecules are on top, and this is the piston of the cylinder. Okay, so you can imagine by increasing the pressure, more gas molecules will go to the liquid phase. By lifting the pressure off, by decreasing the pressure, you will have less gas molecules. So it's explained in this mathematical shape. You will see the gas solubility. By increasing the pressure, solubility increases, and by decreasing the pressure, solubility decreases. That's what it means. And I told you, just like the sprays, just like mostly soft drinks, you can explain it. That's why when you open the bottle of soft drinks, you will hear the psst. That's the pressure of the gas which has been in the liquid and it's being released. All right, you have a problem on slide number 32. It's talking about helium-oxygen mixtures in 2 different pressures, and you should apply the Henry's law for 2 different temperatures, two different pressures, I'm sorry. you will say S1 is KH. It's the same. Henry's constant. It's the same for one type of gas. P1 and S2 is KH times P2, and you need to compare them. So S1 over S2, you cancel this, is P1 over P2. And then apparently you are solving for S2. So cross multiplication is multiplication S1 times P2 divided by P1. Known side over unknown. And then you plug it in to the equation. All right, that's the first type of the first part of this video. In the next part, I will talk about the concentration of a solution, molarity, mass percentage of solute, molality, and mole fraction.